So if this is the circuit for reduced circuit in case of source exchange method, so we can again simplify this circuit as I can draw a current source here and a parallel resistance, this resistance, and the rest of the thing I can consider to be Z. And let me find out the value of this Z. Okay, so this is I naught, this is 1, and the value of the current source is this. Okay, so it is basically 8 plus 2j divided by 1 plus j. Okay, this is plus. So Z here could be written as 1 plus j times 1 minus j divided by 1 plus j plus 1 minus j. So why I have written this? So because these two impedances are connected in parallel, so Z1 into Z2 upon Z1 plus Z2. So if you calculate this, ZZ gets cancelled, and JJ gets cancelled, and finally you get this equals to 1 ohm. So this is 1 ohm. Okay, so now we can find out the current flowing through this 1 ohm resistor. How? By current division rule. So the current that will flow through this would be given by I naught. I naught will be equal to the current source, this I, which is 8 plus 2j divided by 1 plus j times the impedance of Z, which is 1 divided by the impedance of these two. So 1 plus 1 gives you 2. So finally this equals 4 plus j divided by 1 plus j, and finally if you reduce it you will get 5 minus 3j upon 2 amperes. So we got the same result when we try to find it out with the help of the nodal analysis, and we also find it out with the help of superposition theorem. We got the same result. Okay, now let us try to see how we can deal with this circuit, same circuit, with the help of Thevenin's theorem. We'll try to find out the current I naught with the help of Thevenin's theorem. So let me redraw the circuit here again. Let me redraw the circuit here. So there is a resistor here, then an inductor, a current source, then a voltage source, then a resistor, and finally a capacitor, and one more resistor here through which we are interested in finding out the current. Okay, so this is the circuit. This is 1, this is 1, 1, this is J, this is minus J, this is 2 angle 0, this is 6 angle 0. So if we are interested in applying Thevenin's theorem for this particular circuit, so we have to find out two things, one being VTH and the second being ZTH. Okay, so let's start by finding out VTH. VTH could be found out by removing this resistance here. Okay, So this resistance now no longer exists, and we have basically to find out the potential difference between these 2 points. We call it A and here B. So we have to find out VAB, and that will be equal to VTH. So let's apply the voltage division. So voltage division rule. So VTH would be given by, okay, before applying voltage division, let me convert this circuit by applying what is known as the source change. We will try to change the source here, this source, and replace it by its equivalent voltage source. Okay, so if I try to do it, let me draw the redraw the circuit here. So if this would be replaced by a resistance and an inductor in series with a voltage source, and the amplitude of this voltage source would be given by 2 times 1 plus J. Why? Because the current is 2, this is 1, this is J, 1 plus J is the total impedance here. So 2 times 1 plus J gives you the voltage. Okay, so this is in series with this voltage source, which is 6 angle 0 degrees. And finally, this is point A and B, and this is the resistance and the capacitor here. This is 1, this is minus J. Okay, now it's simple to find out VTH. VTH basically we are interested in finding out the impedance, the voltage across here, across these 2 elements, R and the C. So let me write down VTH. So the total voltage, this plus this, would be 6 plus 2 into 1 plus J. This is the total voltage, and this times let me this one be Z1 and this be Z2. Then the voltage across A and B would be Z1 divided by Z1 plus Z2. Okay, so this is equals to 8 plus J, and Z1 is 1 minus J, and again 1 minus J plus 1 plus J. Okay, so this J gets cancelled, and finally if I reduce this expression, I would get 5 minus 3 J volts. Okay, so we are done with finding out VTH. Now our next step would be to find out RTH. Okay, so for RTH, the equivalent circuit, after replacing the sources by the internal impedance, so the circuit would be given by, there would be the resistor, inductor is there, and this would be open circuited. Okay, and this will be short circuited, the voltage source, and then again we have the resistor and a capacitor here, and we are interested in finding out the resistance between the point A, B. So RAB, which will also be equal to RTH. Actually I should write here Z, I'm sorry, ZAB because it is not a pure resistor. We have got other elements also, so basically it should be ZTH. And here also I should write down ZTH and not RTH. So ZTH equals here, this is 1, this is J, and this is 1 again, this is minus J. So this impedance and this impedance, the combination, they are in series. So the equivalent impedance would be given by 1 plus J times 1 minus J divided by 1 plus J plus 1 minus J. So these two J gets cancelled, and finally this will be equals to 1 ohm. So ZTH is this much, 1 ohm, and VTH is this much. Okay, so if I draw the equivalent circuit for the Thevenin's theorem, so it will be given by a voltage source and impedance and the resistor, 1 ohm resistor, through which we intend to find out the current. So this is ZTH and this is VTH. So I naught would basically be equal to VTH divided by ZTH plus 1. So VTH we have found out, it is 5 minus 3J. So 5 minus 3J divided by ZTH is 1 ohm, 1 plus 1 is 2. So finally we get 5 minus 3J divided by 2 amperes. So this is the current that will be flowing through the 1 ohm resistor. So we arrived at the same result which we got by the other methods. Okay.